Okay, I'll explain it. The purpose of this is so we can see that these two areas are the same. And that may not be obvious, but the area under this curve is equal to the area of this rectangle. And it's not necessarily obvious, like I said, but all the area that we have not included here is included in these other areas. So if we could somehow just take all this that's shaded and cram it into this that's not shaded, they would be the same. And I do want you to notice too, the interval is the same. This goes from -5 to 8, -5 to 8. And the heights are not the same. The height here is what, 9? And the height here is not consistent. So we're going to write a little bit here and just sort of make sense of what we're looking at. Mean value theorem for integrals. Whoa, all of a sudden, this is getting wordy. If f is continuous on the closed interval from a to b, and it is, there exists a number c in the closed interval ab such that, okay, often we read math and we get a little lost because it's all these letters and stuff, and so start all over. We have a continuous function on an interval from -5 to 8. There exists some number c, so there's a number somewhere that we're going to talk about, and this is what it is. The area from a to b, this is the continuation of that sentence, by the way. The area from a to b, and we've dealt with that. So if I go from -5 to 8, a to b, there it is. It is equal to this rectangle, the area of this rectangle. Well, the area of a rectangle is base times height. So the base here would be, well, 13. That'd be the distance from -5 to 8. Or the distance from a to b would be b minus a. Well, what about the letter c? Okay. This y value right here, in this case it's 9, or it looks to be 9. It may not be exactly 9, but it looks to be 9. But this y value is c. Oops, I just lied to you by accident. I apologize. That is not correct. It is, I'm going to get it right here. Hold on. Hold your horses. There exists, I'm going to get this right. There is some c value which in this case would be the height. All of a sudden my mind just went blank and I said, oh, this is c. It's not. In this case, actually, this would be c, because at this value we have what we call the average value of the function. You'll see where this is going in a minute. And also at this value. This is also another c value. So I'm not going to label it as a c value. But what I essentially have is some x value. In this case, I have more than one x value that gives me the height of this rectangle, which I will call f of c right there. Okay? So if I were to ask you, what is the height of this? You would say, well, it varies because it goes pretty low, it goes pretty high, it's not consistently the same. And then I said, well, what's the average height? Well, in order to find the average, you would add up all the heights and divide by the number of heights you have. Well, you have an infinite number of heights. Remember when we did this thing where you had an infinite number of rectangles? And well, it's kind of like that. So how do you find that average value that will create equal areas? Glad you asked. In order to do that, it's really a simple fix. We can just solve for f of c. So f of c, and this is so good to know, f of c is the average value of a function on the interval from a to b. So again, the average height here is lower than the highest and higher than the lowest, and it's around here-ish, because we have just as much area not counted as we do over-counted, right? So let's solve for f of c, and there will be some x value that would give us that, or maybe more than one of them. So we solve for f of c, and we get, well, the integral ab f of x dx. I left a gap there because I would divide by b minus a. I personally prefer writing it like this instead of all that over b minus a. I think that's a little bit neater. So we will stop there and then we'll go through some examples.